This is a quick video on the geometry and the proof of how a corner reflector works. It took me a long time to figure this out. So I couldn't find any information about this anywhere on the internet, and math and this physics sort of thing is just a hobby of mine. So I get curious about this stuff and I try to figure it out. And I felt like this was something I could figure out with just logic and simple geometry. And it took me a little while to figure it out, but I eventually got it, I think. I made this video a couple times before, and I ended up taking the videos down because I just wasn't confident in them, and they were, I don't know, they just weren't great videos. So it's been a year or so and I forgot how to do these problems, so I had to figure it out again. And so I'm posting this video again so I can look back on this later. That's supposed to be beta here. Anyways, okay, so this is a corner reflector. A beam comes in on a corner reflector and it always comes back at an identical angle from whence it came, that it came from, I guess you'd say. Anyways, so here's the corner reflector, line going down here. Here's the floor of it here. Laser beam comes in, so this is like a corner reflector on the moon or something. Hits here, bounces, I'll call this angle alpha, bounces back at angle alpha because mirrors are symmetrical. So it'll hit this perpendicular plane right here, reflective surface. I'll call this angle beta, which means it has to bounce back at beta right here. So what I need to do is prove that this alpha is the same, or that this angle is the same at as this angle. So this is alpha, and I have to prove this is alpha. So what I did here, and again, this is just on two-dimensional. I'll do three-dimensional after this. So this is just a two-dimensional plane. So I'll kind of show an example here. The beam's coming in directly here and hitting this directly here. It's not going up at a weird angle here and then coming out there. I'll get to that in a couple of minutes or so. So anyway, so this is alpha, that's beta, and that's beta. So opposing angles have to be the same. So if this is beta, that has to be beta. So I can carry this triangle all the way down. If that's beta and that's 90, that has to be alpha. So therefore, that is alpha, that is alpha. This line continues on up, and that shows that if you draw another imaginary horizontal line here, then that is alpha also. These dotted lines, by the way, are just the imaginary lines. They're not part of the corner reflector. So let's see, so proof is, like I said here, this is alpha, then that means that this angle from here to here has to be alpha, and this is a parallel line, so that has to be alpha. There's also a proof you can use the triangles, where if you use these, I don't know if they're called opposite angles or what, that if this is alpha, that has to be alpha. If this is beta, that has to be beta. And I'll show that proof right here. If you have just a rectangle, or you could use a square, but I'm using a rectangle, so the angles will be different. This line's A, that line's B. That little line here and here means these are both A. Double lines here, that means this is B, and that's the same as here, this is B. So the corner between A and C is called alpha, so that means if this is A right here, and that's C, then that has to be alpha. Same thing with B, line B and C, that is, that corner would be beta, or that angle would be beta. So if I have B here, because this line is the same as that line, so B and C, that angle has to be beta. So beta, beta, alpha, alpha, they're opposite angles on the rectangle, I guess you'd call it. So right here, what I've done is just made a dotted line going across and down for my imaginary lines. If this is alpha and that's beta, by the proof I just showed, that if this is alpha, that has to be alpha. If this is beta, that has to be beta. And then again right here, if this is beta and that's alpha, if that's alpha, then this has to be alpha because it's opposite, which means that has to be beta. So that just shows that this alpha is the same as this alpha, which is the same as that alpha, because they're all horizontal lines and they're all parallel to each other. I'm calling this my parallel perpendicular rule because when you figure this stuff out on your own, you just have to make up your own terms and rules and such. Years ago, when I was in like early college or high school or something, I tried to learn the constellations, but I didn't have a book to tell me the constellations. I just went out and made up my own constellations. And it was kind of fun. I had fun doing it. And then later on, I got a proper astronomy book, and I learned the names of all the, constellations. But I guess I shouldn't feel bad for doing that because, I mean, that's how we got all the constellations. Somebody just has to look at them and make them up. So that's what I did. Anyways, so I just made this up, parallel perpendicular rule. So if any beam comes in here and hits a surface that's going to be parallel, so for example, this line right here is parallel to that line, which is parallel to that line, the angle will always be maintained according to the first plane. So here's alpha, that's coming off at alpha. Here's another plane, so this is alpha. Here's another plane, alpha, alpha, because all these lines are parallel. So that's the parallel rule. And same thing with perpendicular. As long as it hits another surface that's perpendicular, so it comes up here at alpha and it hits here, it'll still be alpha. The same angle here will be maintained. So if, for example, if this is coming in at 30 degrees down, it'll go 30 degrees up. And if it hits, once it hits here, it's still going 30 degrees up in relation to this plane right here, which is the same as right here, which is the same as right here. So whether it hits parallel or perpendicular, that same angle will always be maintained. I guess a thought experiment or a proof on that too is if you take a big football field or a soccer field and you set up a bunch of mirrors on the field that are all just stuck in the ground and perpendicular, shine a laser beam at the mirrors at 0 degrees, so it'll be parallel to the ground. That laser beam will bounce all over the field, but it'll never go up or down. That beam will never go up into the sky, and the beam will never go down into the grass, as long as those mirrors are actually absolutely perpendicular. And now, of course, if they're bent in or out, then of course, it'll deflect the beam, in that direction. But anyway, so the reason I said that is because this is my segue into my three-dimensional analysis of how a corner reflector works. So let's see here. See if I can find my paper here. Okay, here we go. Okay, what I'm going to do is prove that when a beam comes in, if it's going down at 20 degrees, it'll come up at 20. If it goes to the right at 40, it goes to the left at 40. And if the beam's going away from you, then it comes towards you. So here's my corner reflector here. And I got a couple books here to help out with this. So I take my laser beam comes in. If it hits the bottom surface at 20 degrees, it can be oriented in any direction, forming a cone. It'll always be 20 degrees to this surface. So this is 20 degrees, this is 20, all the way around. Right here is 20 degrees as it goes all the way around. So it can be oriented in any direction, but it's 20 degrees to this surface. So if I have it come in at 20 degrees to the floor, it'll bounce up 20 degrees. But I can have it come in 20 degrees to the floor and say 40 degrees to this corner reflector. So it'll be at about this angle right here. Comes down at 20, it'll go up at 40. And it'll maintain that same angle to this plane throughout all of the reflections, because it's reflecting off of perpendicular surfaces the entire time. So it goes down 20, comes up 20, goes to the right at 40. That means it's going to go to the left at 40 degrees, and it's going away from you. But now when it hits the surface, like I said from my parallel perpendicular rule, since all these surfaces are perpendicular, it will maintain that angle of 20 degrees up. It comes down at 20, and when it gets to here, it's still going 20 degrees pointing up. And instead of going 40 degrees to the right, now it's going 40 degrees to the left. So all the angles will be reversed, and that angle will come right back from the direction that it came from. So yeah, that's pretty much it. I think I'm going to leave this video up because I'm pretty confident in the math. It all makes sense. I'm sure if you come across this in a math class, I think they do this in Calc 3 or linear algebra. They do 3D vectors. I'm sure if you come across this, they'll use different terms and teach it a different way, but I couldn't find this information anywhere, and I just had to make it up. It's kind of a weird hobby of mine. So anyways, that's it. And yeah, that's it.